Welcome back. Let's continue on Chapter 11, Section 4, the comparison test. It's another way to discuss the convergence or divergence of a series. So let's just get into it. Let's assume that we have two series of AN and BN. And from 1 to infinity, we start from 2, 3, whatever. So let's say we have these two series, and they both have positive terms. If Bn is a convergent series, and we know An is always less than or equal to Bn. So An is bounded by the Bn's. So therefore, by the assumption that if Bn is convergent, we can say the sum of An's must be less than the sum of Bn's. That means sum of An's also must be convergent. And similarly, if the Bn's are divergent, while the Bn's are in this case smaller than An's, smaller or less than or equal, it means that when you sum up all those ANs, they will be larger than the sum of BNs. Therefore, if BNs are divergent, the sum of ANs must also be divergent. Okay, so be careful about the inequality. You cannot judge the other way. If Bn is divergent and An is less than Bn, then you can't say anything about An specifically. Okay, so if you have An less than Bn and sum of Bn's are going to infinity, that doesn't tell you anything about An's. An could be approaching infinity, or they could approach to some constant L, whatever. So in that case, you can't say anything. Be careful that you use this comparison test properly. And generally speaking, the two types of series that we use to compare are the p-series and the geometric series. What are the p-series? In the last lecture, we talked about the p-series, where the summation of 1 over n to the power p. And we noticed that the only way that this summation is convergent if p is greater than 1. That was one of the examples that we discussed last. And if p is less than or equal to 1, then we had a divergent series. Okay. Geometric series in the form of summation of a r to the power n minus 1. Again, this power, it doesn't need to be n minus 1, it could be n, but generally speaking, this is the format. And n start from 1 to infinity, here n from 1 to infinity. Again, this base doesn't need to be 1, that's why I didn't write it, but you can be picky and say, okay, let's start with 1. If these cases, we know that the geometric series is convergent if the common ratio r is less than or equal to 1, the absolute value of r, and it is divergent if absolute value of r is greater than or equal to 1. Okay, so we use these two normally to apply the comparison test. These are the two common ones. Okay, so here, let's look at this example. Summation of 5 divided by 2n squared plus 4n plus 3. Okay, is this a convergent or a divergent series? Okay, so one thing that you can ask yourself is, can I use the integral test? And the answer would be absolutely. In this case, you could apply the integral test, but the issue would be calculating the integral. That would be quite a torture to calculate this integral. 5 divided by 2x squared plus 4x plus 3 dx. Calculating this integral would be quite difficult, but so instead of doing that, we can maybe apply the comparison test. The more options you have, the better. So what can I say? Let's say an is given to us as 5 divided by 2n squared plus 4n plus 3. And what do we pick as bn as our comparison test sequence? For bn's, we try to pick the simplest form to compare with an. What would be the largest term in the numerator? Not in the numerator. What would be the a reasonable sequence to compare it with an, and that would be in the form of either a p-series or a geometric series. In this case, maybe the simplest one would be 5 divided by 2 to 2n squared. And why do I pick this is now because it's easier for me to compare. What is the relation between an and bn? An, since always has this extra term in the denominator, and that term is always positive, that means the denominator would be always bigger than the denominator of bn. That means an always is less than or equal to bn. Maybe this is not a good choice, then we have to change it, figure out through another test. Okay, so picking bn specifically to be this doesn't mean that it's gonna always work out. But in this case, if we pick bn to be 5 divided by 2n squared, then I can say an is less than or equal to bn. Then how can I say anything about the an? I need to figure out how does bn behaves. So what is the summation of 5 divided by 2n squared? And from 1 to infinity. Is this convergent or divergent? Is this convergent? That is a question. And we can answer that simply by using the integral test. Or we can use the p-series that we already know. We know that this is similar, this summation is exactly the same as 5/2 multiplied by sum of 1 divided by n squared. And when do we get the p-series to be convergent? If this power p is greater than 1, then we have a convergent series. So since 2 as the power is greater than 1, then yes, I have a convergent series. So you don't need to go through the integral test, but if you forget it, you can always apply the integral test. So now I have a convergence bn. What can I say about an? So I can say bn is convergent. Not the bn's. The summation of bn's. Summation of bn's is convergent. Which means this would be some constant, c. And what do I know about the summation of an's? Since an is less than bn, the sum of an must be less than the sum of bn must be less than c. So that implies that this summation also must be convergent. This is by the applying the part 1 of the comparison test. Since bn is convergent and an is less than or equal to b, then an also must be convergent. Okay, normally the choice for bn is simply you pick something related to the an, and it would be either in the form of p-series or geometric series. Not always possible, but if possible, then that would be the case. Here, another example. How about this sequence? Summation of ln k divided by k as k starts from 1 to infinity. Is this a convergent or divergent series? Ask yourself, what would you pick for a comparison? What would you pick as a comparison? I will say, okay, I can pick bn. First, an is ln k divided by k. What do I pick for bn? I'll pick bn to be simply 1 divided by k. Sorry, let me change this to ak and bk. I'll pick that to be 1 divided by k. ln k is less than, it's not always less than 1, but after k being greater than 2, then this is less than 1. K being greater than 3 maybe is enough. So this is true that ak is less than or equal to bk for k greater than 3. Maybe not for the first two, then after that this is always true. And then the summation of ak must be less than or equal to summation of bk. This is for k from 3 to infinity. 3 to infinity. Adding the first two terms, k equal to 1 and 2, it doesn't really make any difference in the behavior of summation of ak. If it was convergent, still would be convergent. If it was divergent, so it still would be divergent. Okay, so now what can I say? Oh, sorry, this is greater than, not less than here. I meant to say because the numerator is larger. Okay, so adding one or two terms, it doesn't really make any difference. So what can I what can I say about the sequence of the series of bk? Summation of bk's is the same as the summation of 1 over k. We already know this from that p series again. 1 over n, 1 over k doesn't really matter. If the power is chosen to be 1, here in the case of p equal to 1, we have 1 over n or 1 over k, then this would be a divergent series by p series. You should say by p series where p equals to 1 in this case. Then I have a divergent series for b case. That means this term approaches infinity. So what do I know about the summation of ak? Summation of ak is greater than or equal to infinity, which means this summation also greater than infinity. That means this summation also diverges. Okay, simple as that. The only thing is that you have to make sure that the bk that you pick is properly applied. If it was the other way around, if this was less than, again, if this was the case, I couldn't say anything about AKs, because then the AKs are less than infinity. That doesn't mean they're not infinite. That you cannot say they are finite or infinite. Okay. Okay. The limit comparison test. This is the limit comparison test is kind of quite similar. The only thing is that it tells you that if you have two sequences, two series an and bn, with positive terms again, and the ratio of an to bn is a constant. If an divided by bn is a constant, then however an behaves, the same way bn behaves. That means it makes it easier that we don't have to check inequalities anymore. We don't need to say, is it less than that or is it greater than this? So in those cases, if an and bn, the ratio of them is any constant, that constant doesn't need to be, sorry, here. This constant must be greater than 0, non-zero. This is the important part. It could be negative also, but since we assume that we're dealing with positive terms, then we don't have negative. So if c is greater than 0, which is a constant, not infinity, then however an behaves, bn exactly will behave that way. So if the series of bn's converges, then the series of an's will also converge. Okay, so just to clarify it, here's a couple of examples. So let's look at the first example, example 1. Here, example 1, it says, find out the summation of, again, we're not looking for so the question is, does this series converge or diverge? So we're looking to figure out the behavior of the series 1 divided by 2 to the power n minus 1. N from 1 to infinity. Okay, ask yourself first, what is an? An is 1 divided by 2 to the n minus 1. Okay, what would you pick similar to an's where they would have a constant ratio? So you have to come up with this bn. And the first thing that you notice is that an is almost a geometric series. So I'm going to pick bn to be exactly the same without that negative 1. This negative 1. I'll pick bn to be 1 divided by 2n. Why do I do that? It's just because now if I calculate this limit, what is limit an divided by bn? As n approaches to infinity, is the same as 1 divided by 2 to the power n minus 1 divided by 1 divided by 2 to the power n as n approaches to infinity. Sorry, limit. And that is simply limit 2 to the power n divided by 2 to the power n minus 1 as n approaches to infinity. And you can simply say, okay, this -1 doesn't really matter. You can divide everything by 2 to the power n if you want, doesn't make any difference. So you would have 1 divided by 1 simply gives you a constant ratio. So this limit would be simply 1. So what does it tell me? That it tells me that however the series of an behaves, the exact way series of bn behaves. However, the series of bn behaves exactly the same. So what do I know about the series of bn's? What is the summation of bn's? N from 1 to infinity, which is summation of 1 over 2 to the power n, n from 1 to infinity. This is a geometric series. If it's not written in the proper way, you can change it to that way, 1/2 to the power n, n from 1 to infinity. That's the same thing. And if you remember geometric series, if you have common ratio to be less than 1, in this case our common ratio is 1/2. This is the common ratio. So if common ratio is less than 1, then we're dealing with a convergent series. So if bn's are convergent, therefore by the limit comparison test, summation of an is also convergent. I can say that just because the ratio of an to bn was a fixed number. However an behaves, bn will behave similar. Okay, so this number as the ratio is important. This number cannot be 0 in infinity. If it's 0 infinity, then you can't really say anything about an and bn unless you have more information. Okay, let's try the second example. Second example is summation of 2n squared plus 3n divided by square root of 5 plus n to the power 5. N from 1 to infinity. Now, here it is important that you figure out a proper bn, because if you can't get any information from the bn, then it is quite useless. So an is given that square root of 5 minus plus n to the power 5. What would you pick for bn? We'll look at an and say, okay, and the largest term here is 2n squared, and the largest term in the denominator is n to the power 5. So I'll probably pick bn to be 2n squared divided by square root of n to the power 5. And if I simplify this, the n squared, this is n to the power 2 square root of n to the power 5, and I can cancel out the n squared. So what do I have as bn is simply 2 divided by square root of n. And why do I pick this bn? It's just because when you calculate the limit would be a constant. So for my comparison, I have to check to see if the limit an divided by bn as n approaches to infinity, is that a constant or not? If it's a constant non-zero, then I can say, okay, whatever happens to bn as a series, the same exact thing will happen to a. And this is limit. Okay, you can calculate this either simply using the largest terms, or you can, if you want, you can apply the Hopital rule, however you prefer. It's up to you. You can multiply root n to the denominator. So basically what you would get is, in the numerator you would get limit to, I'm gonna put this on the n squared root n plus 3n squared root n divided by square root of 2 square root of, by the way, this 2 is not necessary, I just picked it so it's easier for us to deal with. So 2, you can pick bn to be simply 1 divided by, let me make it 1 divided by that just to show it doesn't really make any difference. Here what you have is 5 plus n to the power 5. As n approaches to infinity, what happens is this term and that, they have the same power. They all have n to the power 5. That's the largest term. You can divide everything by square root of n to the power 5. And what you end up with is 2 divided by 1. Or you can apply Hopital rule a couple of times and simplify. Hope that you'll end up with this constant. Okay, you can multiply square root of n again just to get rid of the square roots. It's quite extra work. Okay, so I figured out that the limit is a simply 2. That means an and bn behave the same way. But what do I know about bn's? Summation of bn's is exactly summation of 1 over square root of n. And that is summation of 1 over n to the power 1/2. And what do we know from this theory? This is a p theory where the power turns out to be 1/2. If the power was less than 1, then we had a divergence theory. So if summation of bn is divergent, then since the an and bn by the limit comparison test, you can say by the limit comparison test, summation of an's is also divergent. Again, the good thing about this comparison test is that you don't really need to be, an doesn't really need to be less than bn, or bn doesn't really need this inequality. We wouldn't need this inequality. As long as the limit is a constant, then you can apply the limit comparison test. Okay, final topic in this section is estimating the sum. And this is something we did already, but now we can kind of avoid calculating complicated integrals and estimate the sums by the same idea. Say if you have a sequence of if you have a series of an's and you know this series is convergent and an is less than some other series bn, then the tail of the an, which is rn's, if you remember an plus 1, an plus 2, all those terms, is going to be less than the tail of tn's, because an is less, n plus 1 is less than bn plus 1, n plus 2 is less than bn plus 2, so each term is less than the other. So what does it tell you is that tells you that Rn also must be less than Tn. So if we can find a simpler series for Bn, then we can say, okay, the error is also less than the tail of the other. So this kind of is useful when you don't really want to calculate the complicated integrals. Because if you remember, to calculate this estimate of the error, we had to calculate an integral. So here, for example, find the sum of the first 100 terms and use the sum of the first 100 terms to estimate the error involved in the approximation. Okay, so basically my question is, if we do 100 terms of summation, what would be the error of the error caused by this approximation? So instead of calculating up to infinity, if we go only up to 100 terms, so there would be some tail. The tail would be the sum of those terms would add up to a certain number. That number has a bound. What is the bound? Okay, so normally what would we do is we would say, let's calculate the integral from n to infinity of 1 divided by x cubed plus 1 dx. Right, this would have been Rn. But now calculating this integral is quite complicated, and we don't want to do that. What we can do is we can say, okay, 1 over n cubed plus 1 as an an is similar to bn, where bn is 1 over n cubed. And since the denominator of an is larger, this is less than bn. So instead of calculating this integral, I can say this integral is less than the integral of Tn, the tail of the series of b, which is exactly the same thing, but x to the power 3. So instead of an, we replace Tn. So this, now I can calculate the integral and say, okay, this integral is simply -1. Sorry, let me do the integral so I don't make any mistake. X to the power dx. X to the power -3 dx. And this is negative x to the power -2 divided by -2, evaluated from n to infinity. And that is -1 over 2x squared from n to infinity. Again, you can take a limit and you'll end up with 1 divided by 2n squared. Okay, so if we apply 100 terms, what can I say? I can say the sum of n from 1 to 100 of 1 over n cubed plus 1 will be some number. Whatever that number is, it is close to the result. So this number minus the exact value of this summation. So that summation, let me call it S or R. Actually, we called it S, right? So S minus, and this is S100, minus S100. This is our R100. This R100 is less than T of 100. If you pick 100 as number of terms that you want to add. And that is, we already calculated and say this is less than or equal to, by the way, this was less than, approximately less than. So this is less than 1 divided by 2 times 100 squared. And I believe this is 1.00004 zeros and a 5, I think. Yeah, so I can say, okay, if you do 100 terms, sum of all those 100 terms, it is close to the exact value with this up to this error. Okay, so this gives you an estimate of how close you are to the result. This is the error. It's not the exact error, it's just a bound for error. Okay. Okay, so this kind of the comparison test for the estimates of the sum is still very similar to what we did for the integral test, just to apply the integral test to the compared series. Okay, so let me stop here. We'll continue next time.